Okay, so I'm Kevin O'Brien, Associate Professor in ECS here, and I'm going to tell you about quantum circuits, or you could think of this as diving deeper into the physical system that Will Oliver talked about earlier this morning. And I want to talk about some of the challenges associated with this field and some of the solutions that we can create using our research here. So at a high level, I want to talk about how we can go from this stage of quantum computing, which Will Oliver was likening to the first flight of the Wright Flyer, to the stage of commercially useful applications. And what kinds of technological improvements, particularly what kinds of basic research improvements, do we need to go from the current level of quantum computers to this commercially useful stage? And one thing that you heard this morning, but I want to emphasize, is that quantum computing is really happening now. The current state of the art, we have a few hundred non-error corrected quantum qubits. These are real quantum computers. They're perhaps not capable of doing useful computation yet. For practical applications, it's thought that we will need hundreds to thousands of error corrected qubits, each of which will be made of a number of non-error corrected qubits. And here's a couple of the public commercial companies building these chips. And you might ask, is quantum computing physics or is it engineering? And you can look online and you can find data sheets for quantum computers. So we're seeing that there's indeed a transition to engineering. And another thing to emphasize is that quantity and quality are both required. You need a large number of qubits, and you need qubits with a very low error rate. And small numbers of qubits with high error rates, even with low error rates, this is something that you can classically simulate very easily on a laptop, as Aram was telling you earlier. As you increase the number of qubits, it's thought that there may or may not be near-term applications in this so-called NISQ era. But as you increase the number of qubits, as you implement error correction, then we can utilize the known useful error-corrected quantum algorithms. But we have a long ways to go to get to this point. How far do we have to go? Well, it depends on your assumptions, and these assumptions are constantly changing. If you, for example, assume a 2D nearest neighbor connectivity, a surface code, gates applied at 10 megahertz, error rate of 10 to the minus 5, in this 2018 Quantum Computing Progress and Prospects National Academy's report, it was estimated that it would take 10 to the 6 to 10 to the 7 physical qubits to do something like break RSA using Shor's algorithm. And as the physical qubits improve, as the quantum error correction algorithms improve, then these assumptions may change and the number of qubits may be smaller. But this is really orders of magnitude beyond the current state of the art, but not so far that it's infeasible. So it's a really exciting time to be in this research field. Now, how can we transition quantum computers from physics experiments into useful products? This is a bit of an electrical engineering joke. Do you just substitute I with minus J? But more seriously, quantum computing really needs engineers and their talents and expertise to get to this level. This talk is going to focus a lot on electrical engineering, because I'm in the electrical engineering and computer science department, but really all varieties of engineering experience are critically important in making this transition. So I'm going to talk about some of the research in my group and how that interfaces with superconducting quantum computing. And some of the questions that we're really interested in is, what are the fundamental limits on system performance imposed by quantum mechanics? How can we engineer systems to reach these limits? And can these limits be surpassed? Are we missing some tricks in quantum mechanics that allow us to do better than that? So Ike showed you some Ike and Will showed you some images of superconducting quantum computers with lots of wires going up and down the cryostat. This stage is probably at 10 to 20 millikelvin. The stages are progressively warmer. When in operation, of course, these have metal canisters like a matryoshka dowel, isolating each of the lower temperature stages from the higher temperature stages, and lots of wires going back and forth. And one thing that I don't know if it's clear to people outside the field is that the quantum processors themselves, the chips, they're only a few centimeters by a few centimeters on a side. The rest of this is just control and measurement infrastructure. So anything that we can do, and this is only for order of hundreds of qubits. Whereas we're going to need millions. So there are massive improvements to the infrastructure that are needed. And some of these pieces of infrastructure, they interact in really detrimental ways. For example, your qubits are extremely sensitive to magnetic fields, whereas the circulators and isolators required to protect components from each other, they generate strong magnetic fields. We also need massive infrastructure improvements to multiplex qubit control and measurement, develop non-magnetic isolators and circulators, cryogenic control hardware, as Ike was talking about, placing, instead of having wires going up and down these fridges, placing the control hardware at one of these lower stages. So I'm going to talk about the measurement problem and some of the ways in which you can develop amplifiers to multiplex these measurements to reduce the burden of the measurement chain. So first I want to ask, how do you measure a superconducting qubit? So as background, you may remember this from the first talk, but I'll review it. If you make an LC resonator or LC oscillator, looking at this quantum mechanically, it will have discrete energy levels. And this is not a qubit. This has equally spaced energy levels. Well, this is not a qubit in the way that we would typically use it, because these energy levels are equally spaced. So when you apply a microwave drive, you end up exciting a bunch of different levels. And you excite a coherent state in this resonator, which looks like a classical state in this resonator. So something that will, energy will oscillate back and forth between the electric and magnetic fields at a certain frequency. To turn this into a qubit, we use something called the Josephson junction, which for the purpose of this talk, you can think of as a nonlinear inductor, where the current phase relationship defining the inductance, normally for a linear inductor, the current is related to the flux through the inductor by 1 over the inductance. In a Josephson junction, it's related by this factor we call the Josephson inductance divided by this cosine of phi. And that cosine of phi, when phi gets large enough, this creates nonlinearity, and this is the ingredient that we need to make qubits. And as we'll talk about later, this is also the ingredient we use to build amplifiers to measure the qubits. So when we replace that linear inductor with a Josephson junction, then the level spacing becomes not equal. So notice that this level spacing is different than this level spacing is different than this level spacing. So you can apply a microwave drive and excite the qubit from 0 to 1 and vice versa, or excite it into superposition states of 0 and 1. And there are lots of engineering trade-offs in how you design this anharmonicity. So now we see these two ingredients, this resonator and this qubit. Now you might ask, how do you measure the state of a qubit using one of these resonators? And my students, nor the organizers, would let me bring a dilution refrigerator on stage with me, but I do have something maybe almost as good. So I brought with me this aluminum beverage can, and I have connected to it something called a nano vector network analyzer. This is sort of borrowing from a demo of a electromagnetic engineering class that I teach with Luca Daniel and Jelena Notarosh, previous speaker. And what it does is it sends out microwaves at different frequencies and measures the reflected response. And what I'm plotting here is the amplitude of the response as a function of frequency from 2.165 gigahertz to 2.2 gigahertz, as well as the phase of the response. And we see that there's this dip here, and this dip is associated with the resonance of this resonator. And the way you measure a qubit is you can actually put the qubit inside of this resonator. And that's actually how people did it when the field first started. They would build 3D resonators and physically put the qubit inside of it. And the qubit and the resonator, they interact through this, some of the nonlinearity of the qubit. It's inherited by this qubit-resonator interaction, and it causes the resonator frequency to shift depending on the state of the qubit. So if it's in the qubits in the ground state, it'll be one frequency. If it's in the excited state, it'll be a different frequency. And this is really similar to if I take this can and I just squeeze it a little bit. Notice the can is shifting in response to my squeezing it. Oh, okay. think I deformed the can. Now it's never going back to where it was. But you can see that this can is a really sensitive probe of my fingers touching the can. And this is similar to how you measure a qubit, except now it's a very sensitive probe of the state of a qubit. And originally, the qubit may be in a superposition. It may be in 0, it may be in 1, it may be in a superposition of 0 and 1. And that means that your can may be in one frequency, the other frequency, or a superposition of these frequencies, because the qubit and the can are entangled. So typically, you don't measure this by sweeping the frequency across. Typically, you pick one frequency and send that in the form of a pulse into your system, and then gradually you acquire more information about the state of the can, the resonator. Probably wouldn't use a can in a real experiment. And then that collapses the state of the qubit resonator system into the state of the can in one frequency, the qubit in 0, or the can in another frequency, the qubit in 1. But to do this, you need to use a very small amount of power, because using more than a few photons in this can, in this resonator, it disturbs the state of the qubit in a way that it doesn't retain the state that it collapses to after you measure it. And this is bad for error correction. This is you want your measurement to have this property of being quantum non-demolition. And so that means you need to use this really small amount of power, which creates a lot of practical challenges. So let's shift back to the slides, unless there are any questions about this. Are there any questions about this demo before we go back to the slides? Okay.
So how do you go from the can to these graphs?
Oh, it's a good question. So from the can, so we have this instrument called a vector network analyzer that's connected up to the can with this microwave cable. And it's sending in these microwaves, and it's measuring the reflected response. So what's plotted in the upper left is the S11, or the reflection from the can, on a logarithmic scale. The absolute value of that, 10 log 10 of that, absolute value squared. And away from resonance, you get about the same amount of power back as you're sending in. But as you approach resonance, then you see that a lot of the power is absorbed. But I guess, I don't know, maybe if your question was like operationally, how do you do that? It's just some Julia code that I wrote that takes the data from the vector network analyzer, processes it, and shows it on here. Does that answer your question?
Yes.
Okay, great. Any other questions? Okay, so if we shift back to the quantum system, we have the qubit coupled to a resonator. We send in microwaves at 10 millikelvin. We measure the reflected response, and we see exactly that same effect where, depending on the qubit state, the resonator will shift. It will have an amplitude and a phase response, and you can plot that just like we were doing on the IQ plane, and you can see these two blobs, one associated with the ground state and the other associated with the excited state. But the challenge of doing this is that you want to do this really, really fast. And you want to do this with very high fidelity. And you want to use very small power levels. So measuring small power levels is not unknown to microwave engineering. Your GPS signals are, say, minus 140, minus 150 dBm. But you can't measure your phone can't acquire a GPS lock in 100 nanoseconds. So we need something special to do this, and I'm going to tell you what we need. But first, I want to make an analogy with an analog measurement chain in daily life. So let's say you want to play some music, play the guitar, and you want to share it with someone else that's remote. You could use an electrical microphone to transduce this acoustic signal into an electrical signal. This will have some noise associated with it. It's actually blackbody radiation. And you'll have place a preamplifier to increase the amplitude of that. That preamplifier will add some of its own noise as well as amplify the input noise. Then you'll send this to a secondary amplifier and then to an analog to digital converter, digitize that, have it on your computer, save it, maybe email it to someone. But this ultra-low noise preamp is quite critical because any noise injected by this preamp, it gets it carries through the rest of the measurement chain. Now, to imagine how this is with superconducting qubits, imagine that your microwave emits single photon level signals and your analog to digital converter is 30,000 times hotter than your microphone. So that's similar to the qubit measurement chain, where you have the qubit and the readout resonator, you're sending in around minus 140 dBm at 10 millikelvin. You have a first quantum limited preamplifier and then a secondary amplifier, and then you measure it at 300 Kelvin and perform the qubit state classification. The challenges of this are first that you want to perform these measurements very quickly. You're limited to single photon levels. And second, the qubits are extremely sensitive to thermal photons or other photons in the resonator. For example, to get a state-of-the-art coherence time like those that Google, IBM, et cetera use, you need an average number of photons in your resonator, n bar, of less than 0.002. So two parts in 1,000 of a photon on average in your resonator. You need less than that to achieve the coherence time. And the way to think about that is that your qubit is measured by photons in your resonator. And your qubit doesn't care if you're sending in those photons intentionally or whether those photons are from thermal fluctuations or something else. They all measure the qubit. And at 4K, 4 Kelvin, there are 16 photons in every single mode, and at room temperature, there are about 1,000. So actually, in this can, if I take it and I disconnect it from the source, this is a can of photons where every mode will have about 3,000 photons in it. So people often ask, if there are room temperature superconductors, could you operate a quantum computer at room temperature? And at least if you're operating at, say, sub 10 gigahertz, the answer is no, you couldn't, because the thermal photons would completely swamp the operation. Okay, so how do we actually perform that readout? You might say, just go and buy a semiconductor amplifier. If any of you work in RF or something like that, you can go online, you can order a really good semiconductor amplifier. But it turns out that if you cool these down, these can't achieve quantum limited noise performance. They're typically a factor of 3, usually more, away from the so-called quantum limit, which is the best an amplifier can possibly perform. And this turns out, if we take a look at some of the papers by experts in this, that it results from the challenges of cooling down, dissipating the heat generated by these transistor-based amplifiers as you go to lower temperatures. Because as you go to lower temperatures, there are fewer phonons to help dissipate the heat, so it becomes more challenging. But fortunately, we can use the nonlinearity that creates the qubit to create amplifiers. And I don't know if I'm brave enough to do this like full demo here, but I can give you a little sense of it. So I brought a demo of a parametric amplifier that's a little bit entangled with my keys. So you can think of this as a parametric amplifier. All it needs is some oscillation and some nonlinearity. And if I want to make this move, I can just push it and it'll start oscillating. But that's very inconvenient to do in the base of a dilution refrigerator. But what you can do is, if you imagine this as the microwave you want to amplify, and then you send in a pump wave that changes some parameter of the system, here I'm going to change the length of this string. In the Josephson junction-based systems, you send in a strong microwave pump that changes the properties of the Josephson junction. And what that does is, using this analogy, as you move the oscillator up here, you pull up on the string, and then as the mass is going down, you let it out. You let that extra string out. And then every time it oscillates, it falls a little bit further effectively. And that adds energy to the system. Yeah, it usually takes me a little bit to actually do this with the spring and mass, so I won't do it here, but maybe we can play around with it later. But going back to the superconducting circuits, people can make essentially perfect amplifiers using something called a Josephson parametric amplifier, which is the same physical structure as the superconducting qubit, where it has a capacitor in parallel with the nonlinear inductor, and then it's driven by a strong microwave pump. And this creates a gain in a relatively narrow tens to hundreds of megahertz bandwidth regime. But to reduce the physical hardware overhead, we really want to amplify over a very broad bandwidth. And you can do this by chaining together a bunch of these Josephson junctions to create a transmission line. And this doesn't have a specific frequency associated with it, so it can amplify over a very broad bandwidth. But the question is, can they reach the quantum limit? And this is something that I find a very interesting question. These amplifiers have been demonstrated in a lot of different systems, but so far none of them have really reached quantum limited performance. And some of these amplifiers made using Josephson junctions through a collaboration with MIT Lincoln Laboratory. These are, say, one of the standard amplifiers for superconducting qubit measurements, the bandwidth and dynamic range to simultaneously measure tens of qubits, and they have, and hundreds of them have been distributed worldwide through this collaboration. Here's an example of the gain as a function of frequency, showing very broadband performance. So if we look to the noise performance, I won't go into the details of how this is measured, but it has about half the ideal noise performance. And it'd be really great if these had the quantum limited noise performance, because that can lead to obtaining all the information from the qubit and faster measurements. So if we can break down the quantum efficiency budget, and we can find that some of the quantum efficiency is actually unaccounted for, and some is related to things like lossy dielectrics, which can be improved with better fabrication and engineering. Maybe quick question, since we started like roughly half an hour late, should we try to finish early, or is it okay to? Okay, great. Okay, so in terms of the quantum efficiency, you can view the quantum efficiency of these amplifiers in a perfect single two-mode amplifier. You inject a frequency called the signal. This is amplified, this generates an idler. But in a realistic amplifier, you generate all these other sidebands, all these other frequencies, and they mix in noise. And our idea is that we can build something called we call a Floquet mode amplifier, where we can adiabatically change the nonlinearity of the system. So we can make it like a spring that responds very strongly to the applied field on the two, or very weakly to the applied field on the two sides, or very strongly in the middle. And then if we adiabatically vary the strength of this nonlinearity, then we can generate all these sidebands and then coherently recombine them into the output. And maybe another way to think about this is that if you look at the dynamics of this amplifier, where you inject the signal, it creates the amplified signal in the idler, the blue and the orange line, and this is what you want, but it also generates all this other stuff. But if you go through and you look at this in a different basis, called the basis of Floquet modes, then you find that it looks really simple. And you only have these two modes that do anything useful. So our idea was that we can adiabatically interact with these modes, and it turns out that if you do this, then you can eliminate the contribution of all these noise modes at the output. And when we simulate the response of this device, we see that the quantum efficiency is improved by we can call it quantum inefficiency. It's improved by orders of magnitude when we implement this Floquet scheme. And there's no trade-off in bandwidth. So one thing that I'm quite passionate about in the field of superconducting circuits and quantum information is analysis and modeling. Ike was mentioning how it's kind of a triumph of engineering that the Blue Origin rocket launch, it worked on the first time. And I think that's really key for quantum engineering, building the types of analysis software and the types of methodologies to make these systems work. And one of the things that we contributed to this was building open source EDA tools for nonlinear circuit simulation for these quantum devices. In particular, we built this software package called Josephson Circuits. That's an open source harmonic balance simulator for parametric processes. And it's about 10,000 times faster than the software that the open source software WR-Spice that people are typically using. And we also collaborated with Keysight to compare this with their ADS software, and also to help improve commercial software in this area. So now we want to actually build these things. So we fabricate this using this all aluminum qubit process at MIT Lincoln Laboratories, and we build the device using coplanar waveguide capacitors to reach near zero dissipation. And here's an image of the wafer of these devices. It was fabricated in their foundry. And here we can look at one of the examples of these devices. It's this meandering chain of devices, this meandering transmission line where you inject the signal and the microwave pump on one side, and you get the amplified signal on the other side. And this is in one of the packages that we developed. So if we look at the performance of this, we see that it achieves over 20 dB gain with minimal insertion loss. And when we measure the noise performance, we see that it reaches about 85% of the relative to the quantum limit for phase-preserving amplifiers. So this is getting quite close to being an ideal amplifier, which is really exciting. So a lot of the stuff that we do, it also involves CMOS-style process engineering, where we actually build these things in the clean room in MIT.nano. We characterize tens of thousands of these Josephson junctions in order to improve the reliability so that we can build these quantum computers in a predictable way. Maybe just in the interest of time, I'll go quickly through the last section I wanted to cover is, can we make qubit readout 10 times faster? So as we were talking about qubit readout earlier, we read out a qubit by essentially coupling it to a resonator, sending microwaves into this resonator, and determining the state of the qubit. Well, to maximize the speed at which this happens, you want to have a resonance with a very broad bandwidth. And you also have to have the shift that the qubit creates comparable to that bandwidth. And that shift that the qubit creates, this is something called the dispersive shift. And this is limited by how much nonlinearity you have. And it turns out that that amount of nonlinearity is limited. Our idea was to use a type of qubit that has rather than a quadratic potential with a bit of a quartic potential to it, we wanted to use a type of qubit called a quarton that has a purely quartic potential. And this is really weird from a physics perspective because most things in nature are harmonic oscillators, quadratic potentials. This is something that has no harmonic component. And it turns out that electrically this behaves like an infinite inductor. And when you place this in between two qubits, you can actually turn one of the qubits into a resonator and achieve a very strong nonlinear interaction between these two. And we were able to, using this system, experimentally demonstrate the strongest nonlinear light matter coupling of any quantum coherent system in either superconducting qubits, photonics, et cetera, which potentially has applications, as we discussed in this paper, for improving readout speed by about an order of magnitude. Simply because this nonlinearity is very high, so that leads to really strong interactions. So I think I'm going to wrap up here, acknowledge my group, and maybe if there's time, I'd be happy to take a couple questions. Thank you, everyone.
Being able to measure a qubit more than just whether it's a 0 or 1. Is that the case?
So you can, in the kind of textbook picture of quantum mechanics, you have this so-called ideal projective measurement, where you have your qubit, say, in some superposition state, and then you measure it, and you get a 0 or you get a 1. In real life, measurements take a finite amount of time. So that process can't happen infinitely quickly. So it really is this slow measurement, this measurement process that's continuous, where you gradually extract more information about the state of the qubit, and then the qubit gradually decays into one of its states. So you can actually look at these trajectories of the qubit resonator system. So yeah, it's more complicated than the textbook.
Doesn't that imply that there's a time period where the qubit is in a partially entangled state when it's being measured?
Oh, absolutely. Yeah. You start out with the qubit and the resonator fully entangled, and then you gradually, destroy that entanglement, decohere the state of the qubit resonator system, and extract that useful information. And if you have a really good amplifier, then you can get that information to you. If you have a bad amplifier, then that information may be lost to the environment.
Well, going back to security issues, supposing Eve comes along when you're in the process of measuring your qubit, what happens? That is an external second party is trying to measure it at the same time.
If an external party is trying to measure your qubit, then that can, I guess it depends. That can cause your qubit to, so normally if your system is perfect and there are no eaves or no thermal photons in your environment, then your measurement rate equals your dephasing rate. But if there's an eve or if there are, say, thermal photons, then your dephasing rate can be faster. So it would show up as an increased dephasing rate. Yeah.
Can this partial measurement be useful for anything?
It's useful for a lot of understanding the fundamentals of quantum mechanics. I don't know that it's useful in the sense of like solving quantum chemistry problems, but maybe that'd be a great question to ask in the panel. So I think, in a vacuum, I'd love to answer more questions, but I think in the interest of time, probably we should shift to the panel.